Welcome to MRS Bulletin's Materials News podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Laura Lay. Lithium-ion batteries are currently in widespread use, but their energy density still doesn't compare to more traditional means of powering transportation. One challenge for their use in these applications is that they add to the mass of a vehicle. New developments of a multifunctional battery show that it's possible to have a battery that can also carry a structural load. Whereas previous experiments have used carbon fibre for the positive electrode, the new type of battery uses carbon fibre to construct both electrodes, oriented to impart strength and stiffness in one direction. The negative electrode uses carbon fibre without further treatment, but for the positive electrode, the carbon fibre was coated with a lithium iron phosphate, or LFP. In both cases, the carbon fibre takes on the roles of mechanical reinforcement and current collection. For the untreated negative electrode, the carbon fibre performs a third function. Professor Leif Asp from Chalmers University of Technology in Sweden explains.
So we have two electrodes that are based on the carbon fibers, but only in one case, the negative electrode or the fibers actually the active material. On the positive side, they are coated with the cathode material as active material, but they serve still as reinforcement and current collectors.
The electrolyte is a semi-solid composite. A solution of monomers and electrolyte is heated, causing the monomers to polymerize into a glassy network, with the electrolyte filling a network of pores. The polymer allows mechanical load transfer to the carbon fibre electrodes. Different separators were used between the two electrodes. This latest research is encouraging, demonstrating an energy density of 30 watt-hours per kilogram in stability over up to 1,000 cycles. This performance, particularly the energy density, is likely to improve, but the remarkable mechanical properties of this all-carbon fibre battery demand attention.
We can expect this to increase at least to double within a reasonable year or so. So I would say that we can end up with maybe 40-50% of the conventional lithium-ion LFP-based battery. But of course, one has to realize that this comes with the addition of mechanical load carrying capability. And the modulus of this is actually a stiffer response than you would get from aluminum. So this is a combination of performances that we are after.
This means that future electrified transport options could be designed differently. The design would need to consider how structural components can also be replaced with the battery. To consider how well it would perform as a structural component requires assessment on a case-by-case basis depending on the mechanical load. This necessitates multifunctional analysis at a systems level where both power requirements and mechanical performance are considered. And refining different components of the battery could lead to improvements in performance, both in terms of electrical performance and mechanical.
Within the year, we will see 100 gigapascal modulus, which is then 30% higher than aluminum, and maybe 60 watt-hours per kilogram. I think that's doable. I think also 100 watts per kilogram is doable. We're working on custom making the carbon fibers for the negative electrode. We are working on replacing some of the fibers that we use in the positive to get even higher modulus. We're looking at making the coating on the structure of the battery positive electrode more ductile.
Some of these materials swell and contract during charge-discharge cycles, which can induce stress. Professor Asp's team is now working on multi-scale models to understand these changes. These advances involve a multidisciplinary team which includes electrochemists, materials and mechanical engineers, electron microscopists and physicists working together creatively.
We have all met in this field and together tried to develop. It's super exciting to work in such a diverse team.
This work was published in a recent issue of Advanced Materials. My name is Laura Lay from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org. Follow us on Twitter at MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.